We are now back at the observatory, where we will be talking about lenses, telescopes, and Galileo's astronomical discoveries. In the drama, Hans Lippershey was idling away his time in his optician's shop when he accidentally discovered how two lenses can form a simple telescope, which can be used to view many different things, much to the dismay of his suspicious wife.
It's a lovely day today, isn't it?
What use is that to me, bent over a grindstone? Fed up being your slave.
Lottie! Lottie!
Oh, what on earth is it, Hans? Is there another road traffic accident?
Oh, you can see the stones of the church tower in perfect detail. You must come and look at this.
How very exciting.
If you hold a long lens, with long focus in line with a small lens of short focus, separated by the focal length of the long lens, and you put the short lens to your eye, you see a magnified image. Now,
The lenses we will be discussing are all thicker at the centre than at the edge, or convex. They produce an image which can be focused down onto a sheet of paper, and the image is always upside down. But we'll need the assistance of our friend Porky the Pig to help us show this. Now, Porky has been placed in front of our light source, which in this case is a light projector. The light will travel from the projector through the lens and get focused down onto this sheet of paper. If you look closely, you should be able to see that Porky is upside down. Because this gets focused down onto a sheet of paper, we call this image a real image, in contrast to a virtual image which cannot be focused down, such as the image of your face in an ordinary mirror. What do we call the distance between the lens and the sheet of paper, which produces a sharp image of a distant object, such as the sun? Why can we not look directly at the sun through such lenses and telescopes? Can we use mirrors in the same way that we use lenses?
The image distance for a distant object like the sun is called the focal length. The reason we don't look at the sun through telescopes or lenses is because the light is concentrated down to such a small spot that it could even set fire to a piece of paper. So imagine what it could do to your eye. We can use mirrors to focus light and produce inverted images just like lenses. In fact, modern telescopes use mirrors even more than lenses. We can demonstrate the focusing of light and the production of an inverted image by two concave mirrors facing each other. This produces a real image which seems real enough to touch. So look closely at our little friend Porky as I take the lid off.
Here we have a lens of short focal length of 5 centimetres and a much larger lens with a longer focal length of 50 centimetres. In the film, Hans Lippershey talks about weak and strong lenses, but what do these terms mean? And how did he use a weak lens and a strong lens to produce a simple telescope that magnifies distant objects?
A weak lens deviates light only slightly, so has a long focal length. A strong lens deviates light far more and has a short focal length. We could make a simple telescope that magnifies by lining up a long focus lens with a short focus lens with the short focus lens nearest to your eye. We could use a simple ray diagram to explain this and show how far apart the two lenses need to be. From this diagram, we can see that the separation of the lenses needs to be the sum of the focal lengths. In this case, 50 centimetres plus 5 centimetres, or 55 centimetres. A more complicated ray diagram would show us the formula for the magnification of this arrangement, which is given by the ratio of the focal lengths of the long focus lens and the short focus lens. In this case, it would be 50 divided by 5, or 10 times. A magnification of 10 times is very similar to Galileo's telescopes, or modern binoculars.
Galileo and Hans Lippershey made telescopes that were long and thin and used lenses, like this spyglass. But modern telescopes are relatively short and fat and use mirrors like this reflecting telescope. This reflecting telescope uses a 10 centimetre primary mirror instead of an objective lens and is very similar in size to the ones that Newton made. The mirror is still quite a bit larger than the lenses that Galileo will have used, but is still very small by modern standards. The telescope you saw outside on the roof earlier has got a 35 centimetre primary mirror and so has a lot of light collecting power and therefore produces really good images at the end.